Okay, so welcome back, and in this lecture, we will start with how the circuit is functioning as the clock runs. So, when the clock starts running and each clock cycle, something is going to happen in this circuit. And even though the circuit actually just wanted to show you that we are not explicitly showing the tri-state buffers that I showed you, but to make it much easier to visualize, the control signals, for example, the CP is basically to increment the enable to the counter, right? And EP is basically to enable this program counter or connect this program counter to the 8-bit bus. So EP actually is connected to a tri-state buffer here, which is not shown because otherwise it get too cluttered, like I showed you in the last class, right? So that's very important to remember that. Similarly, LA bar is basically to load the content in the bus to the accumulator, and that is somewhere here, right? Here it is to be shown, but it actually is not explicitly shown because otherwise it looks too cluttered. Okay, so we will see that. And this circuit shown all these connections will actually simply looks like this at the start. Sorry. So it looks like this to start with. Okay, so you have all the circuit components: program counter, memory address register, the RAM, the instruction register, the control unit here. We have not even seen what is inside because we will take it last, because once you understand the functioning of the circuit, expected functioning of the circuit, you have to generate the control signals accordingly. So you have to come up with a digital circuit at the last to make this happen. Okay, so it's not like out of the air we can use it. We are building it from scratch. Nothing is available to you. Okay, and then these accumulators adds up register and output register and the display unit. So only connections which are permanent are this. We do have an 8-bit bus and we have virtual connections with nothing is connected to the 8-bit bus yet. It all depends on the clocks. Each clock something will get connected to the bus and something will connect it in the next cycle and so on. So based on the clock cycle, the connections basically change using that tri-state buffers, which are again triggered by the control signal. So always remember that. Okay, and the only permanent connection is something like to the add subtract, we have the connection from the accumulator and the register B. So add and subtract, the moment you enable them, the addition and subtraction will be happening based on the inputs from these two. So this is hardwired. Okay, so there is no tri-state buffers here, they are always connected. And similarly, output register is always connected to the display, there is no controller. Okay, all others, whether PC gets connected to this or accumulator gets connected to this, all are decided by the control signals which are given to each and everything and is generated from here. So control signals don't get confused. Let me go back to the slide. So this is what we discussed, right? So let me just use that pointer again. So basically these connections will get connected and they are issued by these control signals which are actually showing over here. Okay, so now let's go to the business part of it. So let's start. So as I said, whenever the clock changes, clock cycles, you have a new operation in our microcomputer. So we are going to discuss that in terms of some cycles. So the most important operation in any microcomputer or microcontroller system, the first operation you could say, is something known as fetch cycle. Okay, so we call in general as fetch and execute. Fetch the instruction, so you have to fetch the instruction from the program memory to the instruction register. Okay, so that operation, so you fetch whatever is the content in the program, okay, memory, that first instruction, you fetch that to the instruction. That is what it's known as fetch cycle. So how is that enabled? Okay, so all objective is to get that first content from the memory. So you have 16 cross 8, let's say we are starting from 0000, the first location, you write the instruction there, that instruction has to be stored in the instruction register. So that is what actually known as fetch cycle. So it actually goes in 3 clock cycles, I would say. Okay, so this is the first clock cycle. So whenever there is a first clock comes, what essentially happens is this EP guy, okay, so the enable program counter to the bus guy will become 1. So that means this connection is established. So whenever the EP guy goes 1, program counter gets connected to the bus. At the same time, same clock cycle, you have to issue the control signal such that this guy also, this is LM bar, so LM has to go to 0. So that the load, right? L stands for load. So this bus gets connected to the memory address register also. So what essentially happens in such a scenario is whatever is the content in program counter, it is connected. So it is like now this guy is connected to memory register. That's all. So basically we want to have this content of PC transferred to memory address register, and for that to happen we need to have this connection established, and for this connection to establish you have to issue the corresponding control signals, that is EP has to be 1 and LM has to be 0. In that case this connection is ready, and when the clock triggers or clock cycles, or when that positive to negative edge of the clock comes, or level of the clock changes, depends on whichever whatever way we are going to use the clock for, but whenever the clock changes the program counter value gets into the memory address register. That's the first step or the first clock cycle of your fetch cycle. Okay, so this is the fetch cycle. Don't forget the bigger picture. Fetch cycle means the instruction from the program memory, the RAM has to be brought to the instruction register, and first step towards that direction is the content of program counter. Remember that program counter has the address of the instruction. Okay, all the time in all modern day microcomputers also, microprocessors also, program counter has the memory of the instruction to be executed next. So that basic value, the 4-bit value in this case, gets into the memory address register. That's your first cycle, first clock cycle. So that we call it as address state, because address is getting fetched to the memory address register. Okay, so this, in this case all others are shaded black, and that essentially says they are disabled, they are not used. So that means program counter, memory address register and control unit are active and in this particular cycle, and the bus is connected in such a way that program counter is short circuited with memory address register. Okay, so that's the meaning of it. Now next state is known as increment state. So as the name suggests, increment is to increment the program counter. That means the current address, current value of program counter is already in the memory address register by this step, and now we just increment that by 1. So you enable the counter, next clock cycle, the moment you enable the counter, during the next clock cycle the program counter value gets incremented to 1. So in this case, interestingly, none of the modules are active other than the program counter and the control unit, and none of them are connected to the bus. Okay, so that's an interesting aspect. Correct? I hope you are understanding what I am saying. Okay, so address state is done where the program counter value goes to the memory address register. Then you increment the content of the program counter the moment the initial content is already there in memory address register. So fetch the address, incremented the program counter. The next step is actually what? It's simple, right? The memory address register is already pointing to the RAM. So whatever RAM content should go to the instruction register. That's exactly we are going to do now. So that is known as the memory state, and you can already see it. So the memory address register which already had a value which is coming from the program counter here, and that always points to some location in the RAM. So you enable the RAM to be connected to the bus. So whatever is this program counter value which was already there in memory address register, which is pointing to in RAM, that 8-bit will go here, and that is actually connected to the instruction register. So that is load instruction register signal is also enabled. So this guy RAM is short circuited with instruction register. So that's it. We have done, we have achieved the fetch operation. We have fetched whatever is the content, the instruction in the RAM, in the memory to the instruction register. The whole objective was to fetch this content into the instruction register, but for that we need to have these two things happen at the start. So essentially what happened is, again to reiterate, the content in the program counter got into the memory address register, that is cycle number 1, clock number 1. Clock number 2, the program counter is incremented by 1. Clock number 3, the content of the RAM gets fetched into the instruction register, and that is why it is known as fetch cycle, because you fetch the instruction from the RAM to the instruction register, and these 3 cycles keeps on repeating every time. Okay, so the first 3 cycles, these 3 cycles cannot be avoided. For any instructions, to be fetched from memory to instruction register, which is mandatory for the microcomputer to operate, these 3 keeps on happening every time. So we will talk about now the execute cycle, that is where the real operation happens, but this cycle is to fetch the instruction. So it will fetch first instruction, then the next instruction fetching will also be these 3 things. next instruction will be always this. Then how the instructions changes is because your program counter value is changing, right? So it started, let's make it simple. Let's say it started with 0 0 0 0 initially. Now in this step the program counter is already 0 0 0 1. Okay, so next fetch cycle, when this operation happens, your 0 0 0 1 will go to memory address register. So that's what I meant. Okay, so this is known as fetch cycle. And yeah, in terms of state diagram, you are quite familiar with that in your digital circuits lab. Right, so this is how the based on the clock, how the control signals will change. So let's actually take a look at it. This is address state. T1 stands for this particular state. So at the T1 state, what happened is the EP signal has to go high. So you can see it. So before this clock cycle happens, the EP signal is high and the LM bar is low, right? So that's what happening. And then the all other control signals should be the opposite. So CP is low, CE bar is high, LI bar is high. So no effect on all these three control signals. And remaining all other 12 control signals are there all the time. So the control unit has to keep on generate these control signals, 12 control signals all the time, irrespective of whether they are being used or not. Okay, so that's very critical. So T1 is the address state. So during the address state, only EP and LM are important. So they are gone up and low respectively. And then similarly, T2 state, only CP has to go high. So you can see EP has gone down, LM has gone high. So these has become irrelevant, but CP has gone high. So during this clock cycle, right, during this clock cycle, the CP value is going high. Okay, so excellent. So that's the way the state diagram works. And now you remember the hardware is same. We didn't change anything, but through simple change of control signals, we are able to do these three operations. So what all we did? We transferred the content of program counter to memory address register. We incremented the content of program counter. Then we fetched whatever was there in the memory address register, that address location content data, whatever it is there, that is actually instruction in this case, is passed on to the instruction register. Okay, so this is the fetch cycle. It requires 3 clock cycles, and in 3 clock cycles what we did is actually fetched the instruction from the RAM to the instruction register. Okay, so this is fundamental operation. This remains same for each and every instruction that you want to do. The next 3 clock cycles is known as execute cycle, and that depends on the type of instruction. So if it is LDA, it does something because it needs to do load, right, load operation. If it is add, it needs to do add operation. If it is sub, it needs to do sub operation. It's HLT, it needs to do halting. If it is out, it needs to do the output display and so on. So that is execution. This is fetching. So fetching means irrespective of LDA, add or sub or HLT or out, you fetch that instruction from the RAM to the instruction register. The remaining 3 cycles is execute cycle, which we will discuss now, which is dependent on the type of instruction. So at this stage, the instruction register has that total instruction. It can be LDA something, it can be add something, it can be sub something, which we discussed quite a few times in the last lecture, right? So that instruction is already there in the instruction register at the end of the fetch cycle. Okay, so I hope it's pretty clear to all of you. Okay, and let's move on. Now we will have the execution cycle. Okay, so let me actually put it in the animation mode. So just give me a moment, because if you see everything together, it's not going to help you. Okay, sorry for the small delay. So I just wanted to animate it for you so that it doesn't look crowded. So let's see. So we discussed about how fetching the instruction in the 3 clock cycles in the previous slide. Now here we will take the LDA, the add and sub separately, and out also separately, and see what is happening in that when the instruction is this particular instruction. So let's start with the LDA. Okay, so again this will be 3 clock cycles. So the first clock cycle is something known as this. So what if, again going back to what LDA means, is actually you need to load the content of a particular address given by the instruction. So LDA followed by some address. So you need to fetch the content of that address and put it into accumulator. So that's the important aspect, right? So let's actually do that. So this is the first step. Okay, let me put the pointer again to the laser one. So if you see, the first step is interesting. So you have the instruction, obviously, right? So the instruction register, the last significant 4 bits, that's the address, right? LDA, some 4 bits will come here, right? So that those 4 bits will be the address of the data that you want to put into accumulator. Correct? So LDA will go to the control signal, control unit that will essentially generate the signals that we are going to talk now. So based on if it's LDA, we will issue the next few clock cycles the control signals. Okay, and the data part will actually go into the memory bus, the data bus, and it goes to the memory address register. So the address location of LDA or the whatever LDA plus this address, that address will go to the memory address register. So that's the first step, first cycle. Okay, so for that to happen, your LM bar, okay, so LM has to go low and your EI has to go low, because EI go low means the instruction register, the 4 bits will go to the bus and that will get connected to the memory address register. And then the more significant 4 bits are already there in the control signal. And then, so that's done. So the address is here. Now we need to fetch that address and put it into the this one, right? So let's see what happens. Okay, so the next cycle what happens is whatever is that address which is pointed by the memory address register, the RAM content, so the data corresponding to that particular address will get into the bus and that has to go to accumulator. So you have to make C as low, LA as low, and that content is already there in accumulator at the end of this step. So we achieved it already, because now what we have is LDA some address here, that address was actually put over here, and in this step whatever content in that address in the RAM is already put it into the accumulator. So the last cycle is redundant, nothing will happen. So no control signals, nothing will happen in this particular operation. The reason why nothing will happen is to make it similar, because the add operation, add instruction, which we'll explain the next slide, has the 3 cycles, is occupying the 3 cycles. So that's why LDA, the last cycle is really nothing is happening, but still we'll keep as it is. Now the state diagram is self-explanatory here. So in this step you have to have LM going low, EI going low. Let's see what's happening there. So LM is going low, and then you have the LM bar is here. Yeah, LM is also, LM is here. So EI, right? EI is here. Yeah, EI is actually going here. No, there is something wrong in this. Yeah, I think something wrong in this instruction, because it has to be the other way. Okay, but let's ignore, it doesn't matter. The state diagram, you already know what is the state diagram looking like, right? So basically in this particular case your LM has to go high, go low, EI has to go low, and then only this operation will happen. In this case your CE has to go low. Okay, so that's how it happens. Yeah, sorry. Actually, I made a mess of it. So T1, T2, T3 is the fetch cycle. So you ignore that. You have to start considering from T4, T5, T6. So T4 is what this is T4. Okay. So T4 and LM and EI has to go low. So let's say T4. So T4, your LM is low and your EI is low. Yeah, it's correct. I'm sorry. Sorry for the confusion. So T5 is basically this guy. So T5, your CE has to go low, LA has to go low. So let's say T5, your CE has to go low. Yes, it is happening. And your LA, which is here, has to go low, which is again happening. So that's how it happens. And at this stage, you don't have to worry about, they just need to be, nothing has to be connected at this stage. So it's done. So the first 3 cycles, T1, T2, T3 are the fetch cycle, which remains same irrespective of it is LDA or add or sub. It is just to fetch the instruction from the RAM to the instruction register. The remaining 3 cycles, T4, T5, T6 is specific to LDA or add or subtract or out or whatever, specific to the instruction. And for LDA we explained it something like this. Now let's quickly go to the add and sub. It is something like this. So in the add sub, the thing is, what is expected is some content in the memory that has to be loaded to register B, and then that content in register B has to be added or subtracted with the content in accumulator, and the result has to be stored in accumulator. So it's quite a tedious operation. So let me just write that step here so that it becomes clear to you. So there are 3 steps happening here. Okay, so the basic aim is actually one is to get data from RAM, oops, what is happening, to register B, right? And then second step is add or subtract register B from register A, right? And then third part is basically store result to accumulator or register A, whatever you want to call. So these three operations have to happen, and that's exactly happening in these three steps. Okay, so here what happens actually is get the data from first of all, the instruction register, the address has to go to memory address, right? And the corresponding most significant 4 bit, which is actually representative of add or sub, will go to the control unit. And then in this case, the address, right, which is actually in the location in the RAM, which is getting fetched out, and that is getting stored in B. That's what exactly happened, this step, right? So this step is happening here. So the RAM data is stored in B. So corresponding control signals are enabled. And then in this step, you are actually adding, right? These two A and B are added, and that content is actually stored in register A. Okay, so that's the thing. So add and subtract, this output is now put it into the bus, and that is put it into the accumulator. So this two steps actually happening in this particular case. So let me just ignore the ink here so that it's easy for you. And if you see here, this is a timing diagram. Again, T1, T2, T3 is exactly same, irrespective of, as I said, whether it's LDA or add sub or halt or out. T4, T5, T6 is depending on the instruction. So we can always go back and see for yourself. If you are in doubt, we can always discuss. So that's it. So this is add and sub, and of course there will be a difference at this stage. For add it will be addition, and for sub this will be subtraction. So there is another control signal SU which is missing here, which has to be done by you. So this is just to explain the operation only, that SU determines whether you are doing addition or subtraction. So if it is add, SU will take 1. If it is subtraction, SU will take 0. If you go back and see our control signal again. Okay, so that's it. Now let's quickly see the out operation, which is the simplest of all. So all you need to do is take this out, register A, and then display it in the output register. So it's very simple again. So if the instruction is out, you don't need to fetch anything from data, you just need to display, that's all. So only one cycle is required, but again you keep the other. So T1, T2, T3, again the fetch cycle remains same, only T4 is active here, T5, T6 is not useful here, it just kept idle here. So what essentially is happened is, for fetching and execution, so these two are the fundamental operations, the cycle operations which is happening in microprocessor or microcomputer. Fetching is to fetch the instruction from the memory to the instruction register, and execution is where the real execution happens. And execution 3 cycles are dependent on the type of instruction, whether it's LDA or add or sub or out or halt. Okay, so and the important thing is, like, 3 cycles are reserved for the execution and 3 cycles are reserved for fetch. In fact, fetch requires 3 cycles, execution you ideally don't require 3 cycles, but since the worst, which is the add and sub operation, requires the 3 cycles, we kept it as 3. So totally the most important is 6 clock cycles are required to complete the execution of an instruction. The first 3 cycles are to fetch that instruction, the remaining 3 cycles are required to execute that instruction. But if you see, one particular instruction has to be fully done, you need 6 clock cycles. So that's a critical aspect you take away from here. So this is microprocessor or microcomputer is a synchronous circuit, and it requires clock to have something happening. If clock is not happening, nothing will happen in this circuit. The moment each clock ticks, something is going to happen. And in our case, in this simple 8-bit microcomputer, we have designed in such a way that whenever the clock cycle changes, we have an operation and we require 6 clock cycles to complete the execution of an instruction, including the fetch of that instruction. Okay. So let me just go back to the whiteboard and